On August 1, 2007, an unthinkable tragedy struck Minneapolis, Minnesota. During rush hour, the I-35W Mississippi River Bridge, a vital artery of modern American infrastructure, suddenly and violently buckled, plunging cars and people into the churning river below. This wasn't an ancient, crumbling structure, it was a bridge opened in 1967, considered robust and reliable. What could cause such a catastrophic failure in a seemingly modern marvel? The answer lies hidden within its very design, a story of structural engineering principles pushed beyond their limits. Today, we're counting down the critical factors that led to this disaster. Coming in at number 5, we have the very nature of the I-35W bridge itself, a testament to mid-20th century engineering that masked a fatal flaw. Built as a steel truss bridge, it was designed to carry immense loads across the Mississippi. Its perceived strength came from its robust steel framework, a web of interconnected members meant to distribute forces efficiently. For decades, it served its purpose without incident, handling increasing traffic volumes with apparent ease, embodying the spirit of durable, functional infrastructure that America prided itself on. But beneath this facade of resilience, a critical vulnerability was lurking, waiting for the right conditions to reveal itself. At number 4, we examine the invisible Achilles heel, the bridge's original design from the 1960s. While visually impressive, the initial engineering calculations contained a critical error. The design team, using methods and codes of the era, miscalculated the required thickness of crucial connecting plates within the bridge's main truss. These weren't minor oversight, they were fundamental misjudgments in how forces would concentrate at key structural junctions. This flaw wasn't obvious to the naked eye or even easily detectable by standard inspections of the time. It was a ticking time bomb embedded in the blueprint, patiently waiting for a trigger. Our third critical factor brings us to the gusset plate, the unsung hero, or in this case, the tragic villain, of bridge construction. These are flat, triangular, or rectangular steel plates connecting multiple structural members at a joint, distributing the forces from those members into the main truss system. Think of them as the bridge's knuckles, transferring all the stress. In the I-35W bridge, these plates were crucial for the integrity of its deck truss design, particularly at the U10 and L11 nodes. If these plates aren't sized correctly to handle the cumulative forces, they become the weakest link, jeopardizing the entire structure. And that's exactly what happened. The heart of the design error was that the gusset plates, particularly at critical locations like U10 and L11, were specified as half-inch thick. However, engineering analysis post-collapse revealed they should have been a full 1-inch thick to adequately withstand the anticipated stresses. This seemingly small difference meant a dramatic reduction in the plate's load-carrying capacity. Half the thickness translates to significantly less resistance to bending and shear forces. This wasn't merely a structural weakness, it was a fundamental miscalculation that rendered these vital connections severely deficient from day one, leaving the bridge with a built-in vulnerability. Our second most critical factor is the weight of progress, the construction activities taking place on the bridge at the time of the collapse. While maintenance and repairs are routine, the specific work being done involved resurfacing and other structural improvements. This required placing substantial amounts of construction materials, equipment, and even crew on the bridge deck. This added load, though temporary, was significant. Combined with the regular rush-hour traffic, it pushed the already compromised gusset plates beyond their design limits. It was the straw that broke the camel's back, a cumulative burden that the structure, with its hidden flaw, simply couldn't withstand any longer. Let's quantify that added burden. The construction site on the I-35W bridge included numerous heavy elements, concrete barriers lining the work zone, construction vehicles like pavers and dump trucks, and stockpiles of sand, gravel, and fresh asphalt waiting to be laid. The combined weight of these materials and equipment was estimated to be hundreds of thousands of pounds. This additional, unplanned-for live load was concentrated directly over the weakened gusset plates, particularly those in the main truss. It didn't just add weight, it created localized stress concentrations far exceeding what the undersized plates were designed to handle, even without a design flaw. To understand the collapse, we need to grasp the concept of the yield point in structural engineering. Every material, like the steel used in the bridge, has an elastic range where it can deform under stress and return to its original shape once the stress is removed. Beyond a certain point, called the yield point, the material enters its plastic range. Here, deformation becomes permanent. If stress continues to increase, the material eventually reaches its ultimate tensile strength and then fractures. The I-35W bridge didn't just bend, its steel gusset plates deformed permanently, then catastrophically failed, signifying that the yield point was not just met, but far exceeded. With the undersized gusset plates already functioning at a fraction of their required strength, the added construction load pushed them past their critical threshold. The NTSB investigation concluded that these plates were stressed to more than double their maximum safe capacity. Imagine trying to lift twice your body weight. The plates were experiencing a similar, insurmountable strain. This wasn't a gradual fatigue failure, it was an acute overload. The combination of the inherent design flaw and the superimposed temporary load created a scenario where failure was not just possible, but inevitable. The structure reached its yield point, then its ultimate failure point, within moments. The initial point of failure, the first fracture, has been precisely identified through forensic engineering and simulation. It began with the U-10 gusset plates on the bridge's northern deck truss. These plates, significantly weakened by the design error and overloaded by the construction materials directly above them, buckled. Picture a piece of metal bending and then crinkling under overwhelming pressure. Once the U-10 plates failed, they could no longer effectively transfer the critical forces they were designed for, leading to an immediate redistribution of load onto adjacent structural members. This was the true beginning of the end, a single point of failure triggering a catastrophic chain reaction. Using sophisticated 3D stress models and finite element analysis, engineers have meticulously reconstructed the sequence of the collapse. These models illustrate the domino effect in horrifying detail. As the U-10 gussets buckled, the adjacent truss members, suddenly unsupported, began to deform and then fail. This put immense, unanticipated stress on other gusset plates and connections further along the bridge, which in turn rapidly failed. The collapse wasn't instantaneous across the entire span, but rather a swift, progressive breakdown, propagating outwards from the initial failure point at breathtaking speed, a testament to the interconnected nature of a truss bridge. And finally, at number 1, the heart-wrenching climax, the catastrophic failure sequence itself. From the initial buckling of the U-10 gusset plates, the collapse unfolded in approximately 6.8 seconds. Video evidence and eyewitness accounts confirm a rapid, symmetrical failure. The bridge's center span began to sag and then fractured, pulling down the adjacent sections. The deck truss, once a marvel of load distribution, became a tangled mess of steel and concrete, plunging into the river. This wasn't a slow, grinding collapse, it was an explosive structural implosion, demonstrating the immense forces unleashed when a carefully balanced system is fundamentally compromised and then overloaded. A vivid, terrifying lesson in engineering limits. The National Transportation Safety Board's, NTSB, exhaustive investigation into the I-35W collapse left no doubt about the primary cause. After months of forensic analysis, structural modeling, and reviewing thousands of documents, their final report unequivocally pinpointed the undersized gusset plates as the root cause, exacerbated by the excessive construction load. This wasn't a mystery, it was a clear-cut case of design deficiency combined with a critical overload event. The findings underscored the vital need for rigorous design review and re-evaluation of older infrastructure, especially when significant modifications or loads are applied. The immediate aftermath of the I-35W collapse was a scene of chaos, heroism, and profound grief. But beyond the rescue efforts, the disaster sent shockwaves through the engineering and political communities across the United States. It forced a critical reevaluation of existing infrastructure, particularly older bridges designed under different standards. The collapse became a stark reminder that even seemingly robust and modern structures could harbor hidden dangers. It highlighted the urgent need for a systematic approach to identify and address vulnerabilities in thousands of similar bridges nationwide, transforming how we perceive and manage our vital transportation networks. One of the most critical lessons learned from the I-35W collapse was the absolute imperative of robust bridge inspection protocols. Traditional visual inspections, while important, proved insufficient for detecting deep-seated design flaws like undersized gusset plates. The disaster spurred a demand for more advanced, non-destructive evaluation techniques that could peer beneath the surface. It emphasized that inspections must go beyond superficial cracks and corrosion, delving into the very structural calculations and load-carrying capacities, especially when modifications or unusual loads are planned. This shift demanded greater funding, expertise, and a proactive mindset. Today, advanced structural monitoring technologies are at the forefront of preventing similar failures. These aren't just one-off inspections, they are continuous, real-time assessments of a bridge's health. We're talking about sophisticated systems involving strain gauges, accelerometers, fiber optics, and even drone-based thermal imaging. These tools provide engineers with a constant stream of data, allowing them to detect subtle changes in stress, vibration, and deformation that could indicate a developing problem long before it becomes critical. This proactive approach aims to catch design flaws or unexpected overloads before they lead to catastrophe. The I-35W collapse forced a paradigm shift from reactive maintenance to proactive, predictive care for our infrastructure. It underscored that modern bridges, regardless of their age, require perpetual vigilance. We now understand that the life of a bridge isn't just about its initial design and construction, but about continuous assessment, adaptation to changing loads, and meticulous monitoring. Engineers and policymakers are now collaborating to implement these lessons, ensuring that future generations can rely on safe, resilient transportation networks. It's a commitment to learning from the past to build a safer, stronger future, one structural integrity check at a time. The I-35W bridge collapse remains a tragic but invaluable lesson in structural engineering. It serves as a stark reminder of the profound responsibility engineers carry, the critical importance of meticulous design, the dangers of unforeseen loads, and the absolute necessity of rigorous, technologically advanced inspection and monitoring. By understanding the how and why of this disaster, from the undersized gusset plates to the final catastrophic sequence, we can better guard our future. Our infrastructure isn't just steel and concrete, it's a lifeline, and its safety depends on our unyielding commitment to engineering excellence and vigilance. Stay curious, stay informed, and never stop questioning the strength of what holds our world together.